In this video, we solve problem 7.2.013 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the volumes of the solids generated by revolving the regions bounded by the graphs of the equations about the given lines. Since we are in section 7.2, when we find the volume of these solids of revolution, we're going to use the disk and washer methods. Now, the cylindrical shell method could be used in many, if not all of these cases as well. But since we're in 7.2 and that is about the disk and washer methods, we're going to stick to the methods of that section. So I would start all of these problems in the same way. We want to start by graphing the region bounded by these equations. You always start there. So y equals the square root of x looks like this. When x is 0, the square root of x is 0. Square root of 0 is 0. So 0, 0 is on our graph. When x is 1, y is the square root of 1, which is 1. When x is 4, y would be the square root of 4, which is 2. And we see something like that. Y equals 0 is the x-axis, so that's right there. And x equals 3 is a vertical line. So our region is the region bounded by this curve and this line. And this line, y equals 0, is the x-axis. So it's that region inside there. Now we're asked to take this region and revolve it about the x-axis. So what I would do next is sketch the reflection of the region about that axis. So if we're over here and we revolve it around the axis, what we're going to see is the same sort of shape down here. And then after we sketch our reflection, we want to slice perpendicular to the axis. To form a disk or a washer. Now, because there is no gap between the original region and the axis, what we have are disks rather than washers. So we're going to decide between the disk or washer method. Since there's no gap, this is a disk method problem. And then we're going to decide whether we're integrating with respect to x or with respect to y. And that has everything to do with the width of our little disk. That width is a tiny distance in the x direction, so that's a delta x there. So we're going to be integrating with respect to x. So after we do these, after we sketch the region, sketch the reflection, and then slice perpendicular to the axis, and then we make our decisions regarding the disk or washer method or whether we're integrating with respect to y or with respect to x, then we want to find the volume of a typical or representative disk in this case. So this disk looks like this. The volume is the area times the thickness of the disk. Area of a disk or area of a circle is pi times the radius squared. And we want that radius in terms of x because we're integrating with respect to x. Now the radius always starts at the axis and goes to the outermost edge of the disk or the, It goes to the outermost edge when we're talking about the disk method. The radius is the same as the height of that vertical rectangle. Since that is a vertical distance, we're going to take our top y value and subtract our bottom y value, but we want those in terms of x because we're integrating with respect to x. The top y value is given by the square root of x. So if we're talking about the ith disk, we're going to write the square root of x sub I, and the bottom y value is just given by the equation of this horizontal line, which is y equals 0. So we have that there. And so we're saying find the volume, which we're calling v sub I. That's the volume of the ith disk. That's our and that's the ith disk is our representative disk. So we're going to take our square root of x sub I and substitute it in there to find the volume of that disk. When you square a square root, those two operations undo each other, and we just end up with this. And then the volume is the limit as the number of disks goes to infinity, or alternatively as the thickness delta x approaches 0 of the sum of all of those volumes. Assuming that we have n disks, it's going to be that sum of v sub 1 and v sub 2 and v sub 3 all the way through v sub n. Which can be represented this way, which can be represented this way. And this is a special case of a Riemann sum. So in the limit, we get this. We have pi times x as our integrand. Delta x will become infinitely small, so small that we call it dx. And then we need bounds because this is an antiderivative. And this, well, that's going to be a finite number for the x sub I in this interval from x equals 0 to x equals 3. If we're on the interval from 0 to 3, x starts at 0 and stops at 3. Those are our limits of integration. And now we can evaluate this integral using the power rule. So we found the volume of a representative disk. You set up the definite integral. By taking the limit of the sum of the volumes of those n disks, and we get this. And I know if you're thinking, oh, that's not rigorous, I know that this is just a special case of a Riemann sum, not a true Riemann sum. Okay, so this is equal to this, and we're going to use the power rule, add 1 to the exponent, and divide by the new exponent. That's the first step when you're evaluating a definite integral. This is called the fundamental theorem of calculus. I'll abbreviate that FTC. And then you substitute in the bounds 0 and 3 and subtract. 3 squared is 9. So we're going to have 9 times pi over 2 minus 0. So the volume is 9 pi over 2. Okay, great. Now we're just going to repeat this process again for the y-axis, the line x equals 3, and the line x equals 9. And then we'll see how revolving the region around different axes result in different volume equations or different volume integrals, and then give us different volumes. So same region, but instead of revolving around the x-axis, which is what we did here, now we're going to revolve around the y-axis. So we're going to revolve it this way. So we start in the same way. We sketch the region. Y equals the square root of x looks like this. X equals 3 is right there. Y equals 0 is still the x-axis. So I have x equals 0, y equals 0, and that's on the x-axis. And the region that we're looking for is bounded by that curve, and that curve. So our region is this region here. Now we're going to revolve it around the y-axis. So we're going to sketch the reflection of our region about the y-axis. And then after we do that, we're going to slice perpendicular to the axis and then make some decisions. We're going to choose between the disc or washer methods and whether we're integrating with respect to x or with respect to y. Okay, so what we would see is approximately something like that in the reflection. When I take this and I revolve it like that, it'll look approximately like that. That's my sketch. And now I want to slice perpendicular to the axis. And there's a gap. There's a gap between our axis and our region. So that means we are looking at washers rather than discs. And the thickness of our washer is a tiny vertical distance. So we're going to integrate with respect to y. All right, so our volume is the area of the washer times delta y in this case. And the area of the washer involves taking the area of the larger circle and subtracting the area of the smaller circle, the inner radius, so I'll call a little r sub I. So we have the area of the big circle minus the area of the little circle. Factor out pi. Got that right there. And now we just need to find the outer radius and the inner radius, or if you prefer the larger radius and the smaller radius. You have radii for two different circles, that circle and that circle. And both of those are going to involve a difference. Now the outer radius starts at the axis and it goes out to that outer edge of the disc, and I would always use the outer edge of the disc in the original region. So it's the distance from there to there. And I think we can all see from this picture that it doesn't matter which slice we're talking about, that radius for the outer disc is always going to be 3. But in general, if I were trying to find that outer radius, since it's a horizontal distance, I'm going to take my x value on the right and subtract my x value on the left, taking the larger x value and subtracting the smaller x value. So that's x equals 3, and I'm subtracting x equals 0, which of course just gives us a 3. And then for the inner radius, it's very similar. I wish I could sort of zoom in. We're going from the axis to that innermost edge of, or that inner edge of our washer. So we're going from there out to there, or there to there. Now that is still a horizontal distance. So we still want x on the right minus x on the left. But x on the right is given by the x value on this curve. And remember, even though we want an x value, we want an x value on the right and an x value on the left in terms of y. So I need the x value on this curve in terms of y, which is easy enough to find. Just solve this for x by squaring both sides. It turns out that x is equal to y squared when we're on that curve. So x on the right is y squared. We're talking about the ith disk, so I'll call that y sub I squared. And x on the left is x equals 0. We're on the y-axis. So our inner radius is y sub I squared. So the outer radius is 3, inner radius is y sub I squared. And so now we have, if we simplify, pi times 9 minus y squared squared, which is y to the 4th, times delta y. And so our volume is pi times the integral of 9 minus y to the 4th with respect to y. And we're going to integrate from one y value to the other. Well, x goes from 0 to 3, but y goes from y equals 0 to whatever that y value is right there. Well, when x is 3, if we're on this point or at this point of intersection, y is going to be the square root of 3. So y goes from 0 to square root of 3. Those are our limits of integration. So what did we do? We chose the washer method, and we realized that we were integrating with respect to y. Then we found the volume of the ith washer. And then if we add up those volumes and take the limit as delta y approaches 0 or as the number of washers goes to infinity, we set up the appropriate definite integral. And now we just want to use the power rule to anti-differentiate and then use the fundamental theorem of calculus to compute this definite integral, compute the value of the definite integral. So we've got a pi there. The antiderivative of a constant is our constant times our variable. In this case, our variable is y. Over here, we're going to add 1 to the exponent and then divide by the new exponent. So we're adding 1, so we get 5, and then we'll divide by 5, which is the same as multiplying by 1/5. And then we evaluate from y equals 0 to y equals the square root of 3. So we have pi times 9, evaluated at square root of 3. We're going to have 9 times the square root of 3 there, minus 1/5. Then we've got the square root of 3 raised to the 5th, minus all of this evaluated at 0, which is just 0. Now, if you want to, you could write this as the square root of 3 times 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 the square root of 3. That's obviously a 3, and that's a 3. So I've got 3 times 3, which is 9, times the square root of 3 there. So I have 9 square roots of 3 minus 1/5 of 9 times the square root of 3. So we're going to end up with 4/5 of 9 times the square root of 3. And then don't forget your pi. And of course, we would simplify that to 36 pi times the square root of 3 over 5. All right, so that was our second one. That was part B. Let's keep going. Now we want to take this region and we want to revolve it around the line x equals 3. So far we've revolved it around the x-axis, the y-axis, and now we're going to revolve it around a line parallel to the y-axis, x equals 3. So instead of flipping it this way, we're going to flip it this way. We take this region and we're going to flip it over here. But we do the same thing. We start by sketching. Always sketch, because the graph is going to tell you exactly what you're supposed to do. The geometry really helps us to develop an intuition for what's going on. So there's y equals the square root of x. X equals 0 is or y equals 0 is the x-axis. And we can see, just like before, when x equals 3, y is equal to the square root of 3 at that point of intersection. And now we're revolving it around the line x equals 3. So due to symmetry, we're going to see points that look like this on the interval from 3 to 6. And I'm going to try to make it look symmetrical. Sometimes I succeed and sometimes I don't. All right. So we have that there. So we sketch the region. Sketch the axis and the reflection about the axis. In this case, that axis was x equals 3. Then we want to slice perpendicular to the axis. And then we want to make some decisions. We're going to choose. I'm going to say, is the disk method or the washer method appropriate here? And then we're going to ask ourselves, are we integrating with respect to x or are we integrating with respect to y? Well, when I slice perpendicular to this axis, like I'm slicing a loaf of bread, I get something that looks like this. Now there are no gaps between our original region and the axis. Since there's no gap, that means we're going to use the disk method. If there is a gap, we use the washer method. And then we look at the thickness of the disk. That's a tiny vertical distance. So we're going to integrate with respect to y. Once we know that we're using the disk method and we're integrating with respect to y, we can state the formula for V sub I, the volume of the ith disk. Volume is going to be the area of the disk times delta y in this case. And the area of a disk is just the area of a circle, that's pi r squared. So we just need to find the radius, and we need that in terms of y. Now, I didn't list this step on the others, but of course we have to find the radius so that we can find the volume. In this case, now the radius is horizontal. Now careful here, when you're computing the radius, you always want to start at the axis and then go to an edge of that disk or washer. So you're going to the inner edge when you're talking about a washer. You're going all the way out to that outer edge when you're talking about a disk or the larger circle in the washer, on the washer's face. But I say be careful because you might be tempted to go to the right. You may be comfortable just drawing an arrow from here to here. You don't want to do that. You always want to go from the axis to a point on the outside edge of the disk in the original region. So the radius is going to be that distance from there to there, because that's where our rectangles come from. And then we're imagining rotating that rectangle around and it's giving us this disk. And it's a horizontal distance. So we need our x value on the right minus our x value on the left. And we want those in terms of y. Well, our x value on the right is just 3. And our x value on the left is the x value on this curve. And we already did that on the last problem. When we're on the curve, y equals the square root of x. If we square both sides, we know that x is equal to y squared. So x on the left this time, x on the right minus x on the left is y squared. And if we're talking about the ith disk, that's y sub I squared. So we substitute this in for our radius over here. So we stated the formula, we found the radius, and then we used the radius to find V sub I. And then we imagine adding all of those together and taking the limit as the number of disks goes to infinity, or alternatively as the thickness of each disk approaches 0. And we are able to set up the definite integral. In the limit, we've got pi times 3 minus y squared, quantity squared. Delta y becomes a dy. And we're integrating from one y value to another because we're integrating with respect to y. So we look at our region, the original region, and we say y starts at 0 and it ends at square root of 3. So we're going to integrate from 0 to square root of 3. Okay, great. Now we just have to evaluate this and use the fundamental theorem of calculus to evaluate this. And then we'll be done with part C and we can go on to part D. Now, whenever we look at an integral, we always have to ask ourselves whether or not we have a basic rule for what's there. And we don't have a basic rule for this because we have something raised to a power. Now, the next thing I might think to myself is, can I use U substitution? If I've got a function nested inside of another function, I might think U must be 3 minus y squared. U is always the inside function, right? Now, we know that that will only work if we can compute du, compute the derivative of that inside function, and see that as a factor outside. But the derivative of 3 minus y squared is actually negative 2y, and there's not an extra y out here. Since there's not an extra y, u sub is not going to work. So then you say, okay, what do I do next if u sub doesn't work? Well, then you go to your 9 techniques for algebraic manipulation of integrands. And those techniques allow us to write the integrand in a new form so that our basic rules apply. And one of those techniques is to expand a binomial squared. So that's what we have here. We've got 2 terms and it's squared. So we don't have a rule for that, but we do have a rule for the antiderivative of a polynomial. We can just antidifferentiate term by term. So we'll write this twice in FOIL. I'll factor out the pi as well. First times first is 9. Outer times outer is negative 3y squared. Inner times inner is just like it. So we're going to have negative 6 of those y squareds. And then last times last is a positive y to the 4th. And now we're going to antidifferentiate. If I have a constant here, the antiderivative of a constant with respect to y is that constant times y. Bring your power down, add 1 to the exponent and divide by the new exponent. Over here, add 1 to the exponent and divide by the new exponent. And substitute in y equals 0 and y equals square root of 3 and subtract. So we are expanding the binomial squared so that we can apply our basic rules. And then we just use the power rule to antidifferentiate, or the constant rule. And then we'll use the fundamental theorem to evaluate this. We take the upper limit and the lower limit, we substitute those both in and we subtract. And of course, 6 divided by 3 is 2. So at the upper limit, we'll have 9 times the square root of 3 minus 2 times square root of 3 cubed. That's square root of 3 times square root of 3 times square root of 3. And then we have 1/5 times square root of 3 to the 5th. Now you don't have to write it out this way. I just think it makes it easier to explain what it is that we're doing. When we substitute in y equals 0, we get 0. Square root of 3 times square root of 3 is 3. So I've got a 3 here and a 3 here. So what we end up with is pi times 9 times the square root of 3. Then I have a negative 2 times a 3. That's negative 6 times the square root of 3 there. And over here, I've got 9 times the square root of 3 times 1/5, or 9 square roots of 3 over 5. So I'm thinking of this as 5/5 times 9 square roots of 3, and I've got 1/5 of those over here. So that's actually 6/5 of 9 times the square root of 3. And then for this 6 times the square root of 3, I might write that as itself over 1 and get a common denominator by multiplying by 5 over 5. And this is what we get. So we've got pi times 54 square roots of 3 over 5 minus 30 square roots of 3 over 5. So that's going to give us 24 square roots of 3 over 5 times pi, or you might write it as 24 pi times the square root of 3 over 5. That's a lot of arithmetic. If you prefer, you can use a calculator, but if they want an exact answer, and we often do when we're solving math problems, when we're not dealing with application problems, we often want an exact answer. This is how we might find the exact answer. There are lots of other ways to do the arithmetic here as well. Okay, last question. Last part of this question. I've got quiz solutions here. There we go. Same region? And this is not to scale, but we kind of have an idea what that shape is already. Oops. Now we were asked to revolve the region about x equals 9 next. So this is not to scale. We'll say x equals 9 is over there. What we would see is the mirror image of this across x equals 9. It's kind of like that. So there's our region, there's our axis, x equals 9, and then our reflection is over here. So we always start by sketching. You sketch the region, sketch the reflection, and of course you want to sketch the axis as well. And then you want to slice perpendicular to the axis. Now, since there's a big old gap between our region and our axis, this is going to be a washer method. So you choose between discs or washers based on whether or not there's a gap. Since there is a gap between the axis and the region, we choose the washer method, and then we decide whether we should integrate with respect to x or with respect to y based on the thickness of our disc or washer when we slice perpendicular to the axis, like you're slicing a loaf of bread perpendicular to that axis. And in this case, the thickness is a tiny vertical distance, which would be delta y. Okay, so now we need to state the formula for the volume of a washer. I'm sorry for the awful picture of a washer. We've got that right there. The outer radius is denoted by capital R. The inner radius is denoted by lowercase r. Volume is going to be the area of that face times delta y. And the area of the face of this washer is just the area of the larger circle minus the area of the smaller circle, which is pi r squared in both cases, just with different radii. Many people like to factor out the pi, including me. And then we see this. We just need to find our outer radius and our inner radius. Now, to find our inner radius, we go from the axis to the innermost edge of our washer. Notice that the inner radius is going to be the same for all of these. It's the distance from here to here. It's going to be an x on the right minus an x on the left. But x on the right is always 9. And x on the left is always 3. So the inner radius is going to be 6 every time. And then we need our outer radius, our larger radius. Well, that changes from slice to slice. But we're still going to use an x value on the left and subtract an x value on the right. I said that backwards. X value on the right minus x on the left, larger minus smaller. The larger x value here is 9. The smaller x value is the x value on our curve. Remember, our curve was given by y equals x squared, or sorry, y equals square root of x. So if we are solving for x in terms of y, we would square both sides and we find out that x is equal to y squared. So we want x on the left, but we want x on the left in terms of y, which means we get y squared. And if we're talking about the ith disk, we'll use y sub I squared. So that is our outer radius. And then we imagine that's the volume of one of our disk, our ith disk, and we've got n disks. So you want to add those up and you want to take the limit as either the number of disks goes to infinity or your delta y approaches 0, and you get an integral. So we have the integral of pi times that expression. We don't need the i's anymore because we're saying we're going to cover every possible y value. So this is going to be 9 minus y squared quantity squared minus 6 squared, which is 36. And we need to integrate from a y value to a y value because we're integrating with respect to y. For our original region, y starts at 0 and it goes through y equals square root of 3. I have a basic rule for this, but I don't have a rule for this because the derivative of this is negative 2y and there's not a factor of negative 2y. So we have to write that twice in FOIL. Or alternatively, you can remember that formula for a minus b quantity squared and apply that here. First times first is 81. Outer times outer is negative 9y squared. Inner times inner is just like it. So we've got 2 of those. Last times last is y to the 4th. We're subtracting 36 from that. So we've got 81 minus 36. That's 81 minus 30. That's 51. 51 minus 6 would be 45. Is that right? Yeah, 45 plus 36 is 81. So we have that there. And now we're ready to anti-differentiate and then plug in the limits. So we're ready to apply the fundamental theorem of calculus to evaluate this now. Now you don't always have to expand the binomial squared, but we have to expand squared binomials if we don't have a rule for that. We didn't have a rule for this, but we have a rule for this. So now we can apply that anti-differentiation rule. Differentiate. There we go. The antiderivative of a constant with respect to y is the constant times y. Bring your constant down here. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Substitute in 0 and square root of 3 and subtract. 18 divided by 3 is 6. So we're going to end up with 45 times the square root of 3 minus 6 times square root of 3 cubed. It's square root of 3 times square root of 3, which is a 3, times an extra square root of 3. Plus 1/5 times square root of 3 to the 5th. That's square root of 3 times square root of 3 times square root of 3 times square root of 3. That's another 3 times another square root of 3. So we have this now. So we've got 45 times the square root of 3 here, minus 18 times the square root of 3. And then we've got 9 times the square root of 3, but divided by 5. Well, if we want to do this inside the parentheses, we can do 45 minus 18. Well, I know that 45 minus 15 is 30, and then 30 minus an extra 3 would be a 27. So this is going to be a 27 square root of 3. And then I'm adding 9 times the square root of 3 over 5. So I might want to get a common denominator. So I'll write that as itself over 1 and then multiply by 5 over 5. And then we end up with 27 times 5. Well, that's going to be the same as 20 times 5, which is 100, plus 7 times 5, it's just 35. So we'll have 135 square roots of 3 over 5, plus 9 square roots of 3 over 5. And 135 plus 9 is 144. So we end up with 144 times pi times the square root of 3, all divided by 5. Now again, You could always use your calculator for this arithmetic, and people are going to do the arithmetic in different ways. And of course, when we evaluate that at 0, we get 0. So we just did the f of b minus f of a, evaluate the upper limit and lower limit, and then subtract and simplify. Okay, I guess we handled all 4 axes. So that's the end of the video. Remember, the way you want to start these is by sketching the region, sketching the reflection of the region about the axis, and then slicing perpendicular to the axis. Then you're going to make a decision about whether you're using a disk or washer method, or whether you're integrating with respect to x or with respect to y. If there's a gap between your axis and your original region, it's a washer. If there's no gap, it's a disk. If the width of your disk or washer is a tiny distance in the x direction, you integrate with respect to x. If the width of your disk or washer is a tiny distance in the y direction, you integrate with respect to y. Once you've made these choices, you can state the correct formula for your volume, find the radius or radii, depending on which case you're in, and then eventually use the volume of the ith slice to set up the integral. Then you just evaluate the integral using the fundamental theorem of calculus, and if you've got a binomial squared, you might have to write it twice in FOIL, or alternatively apply the formula for a minus b quantity squared.